Okay. So I'm speaking on the potential for using ACH-based water treatment residual for the mitigation of Pfas that may be leaching from biosolids. So I'm from Purdue University. I work in the Dr. Lee Research Lab. So just a brief introduction of how PFAS get into our water treatment residuals. So PFAS from the environment, everywhere from our homes, municipals, from the firefighting foams, they all end up in the water treatment plant facilities where they are being treated. And then from these treatment plant facilities, there are 2 to 3 products that ends up there, the biosolids and the water treatment residuals. So water treatment residuals are coagulants that are used in water treatment process to coagulate contaminants, especially organic contaminant that may be in the wastewater that is coming to the treatment plant. And so after they've been used as coagulants, the end product of them is this dirty, dark-looking residuals that are being disposed of by the treatment plants. So majorly there are two kinds of residuals that are used by treatment plants. We have the aluminum sulfate, and we have the iron 3 chloride that is usually used. And then more recently, the ACH, which is aluminum chlorohydrate, is now being used by the treatment residuals. Basically, these ACH-WTRs have been found to be more useful in terms of the amount of coagulant properties it can do based on the number of cation charge it has. It has more basicity and more cationic charges than both the aluminum and the iron treatment residual, so it's gaining more use in the water treatment plant process. So after it's been used for the water treatment, the dirty coagulant, which is now the treatment residuals, have been shown by studies to sorb heavy metals that may be leaching out from water sources such as selenium, mercury, arsenic, and also it's been used in land applications to sorb out soluble phosphorus that may be from biosolid or soils or leaching out into streams. So based on these cationic properties, we decided that we could use it for PFAS leaching from biosolids. So now, why biosolids? So this is a graph from the EPA site. So of all the biosolids produced in the United States, 4.7 million dry metric tons, in 2019, 51% of it ends up being land applied. So, a large chunk of the biosolid produced are land applied. Of course, biosolids are an excellent source of nutrients to the plants. Plants love biosolids because they slowly release nutrients and carbon source, which is good for the plants. But in all of this, the major challenge there is biosolids have been shown to contain PFAS, and our agricultural system, which is like the biggest consumer of biosolids in the United States right now, is thus vulnerable to PFAS accumulation in this process. So what are the objectives of my research? So the first thing is to quantify the PFASs in the biosolids and treatment residual. And then from there, I'm going to do some desorption studies on the treatment residual to find out if the initial PFAS that are on the treatment residual is leaching out. This is going to determine if we can do further sorption studies with the treatment residuals. And then from there, we're going to quantify PFAS sorption using the ACH-WTR in biosolid-derived porewater. And we did some batch sample experiments to figure this out. So my residual PFAS on the treatment residual, that's the ACH treatment residual. So for all of the analysis that I'm going to talk about in this research, I did solid phase extraction for them, and the quantification was on a PFHx triple TOF, and the analysis was done on PFHx software. So for the PFAS, we found out that the leading PFAS on them are not are not so much, and then from the desorption experiment, most of them are not dissolving, and PFOA, PFNA were below LOQ. The two compounds that dissolved were PFBS and PFOS. PFOS at 2% and PFBS at 27%. So with this data, we found out, okay, it's somehow safe to proceed to use this ACH treatment residual as a mix with biosolid to solve the PFAS that may be leaching out from the biosolids. So then I proceeded to make out my pore water that was used for the biosolids by mixing it with in a 1:5 ratio of biosolid with the ionized water in the lab, and then checked the initial the pore water concentration of PFAS in them, and we decided to spike it further to use it for this analysis. So the concentration of the PFAS in the pore water used for this analysis are within 250 to 700 nanogram per liter. Having done this sorption, so batch sorption experiments were done, which was rotated for 60 rotation per minute for 48 hours, solid phase extraction. From this plot here, we could see that our sorption was increasing with increasing chain length, and that is somehow significant in the sense that longer chain compounds would prefer to sorb to the treatment residual, while the shorter chain compounds, which are more hydrophilic rather, would prefer to stay in the aqueous phase of the pore water. So we could see PFBS here, PFBS and PFOS. We could see that PFOS was sorbing more, while PFBS was sorbing less. But irrespective of that, as we increased the amount of treatment residual, because we used different treatment residual from 0.6 gram per liter to 56 gram per liter, as we increased the amount of the treatment residual, more and more PFASs were sorbing. So this is quite indicative and shows that the treatment residual could be a good sorbent material to be used for PFAS that may be sorbing out from biosolids when they are allowed applied. Among the perfluoroalkyl acids, we could see that PFNA also sorbed at a significant level, most of them at around 90% sorption, at the highest amount of treatment residual used compared to the shorter chains. And we went further to do a desorption experiment to see if the amount of if the sorbed PFAS on the treatment residual after sorption is going to dissolve out. This is necessary to be sure of the usability of the treatment residual. So what we saw was that the shorter chains seem to be sorbing out more, unlike the longer, to be dissolving from the treatment residual, unlike the longer chains. So the longer chains were dissolving less with increasing amount of the treatment residual. Take, for instance, PFOS here at the highest amount of treatment residual use, which is 56.9 gram per liter. We saw a little amount of desorption, about 2% desorption, compared to when it was 0.6 gram per liter, we saw about 25% desorption. So as we increased the treatment residual, less and less desorption of the PFASs were happening. And this is quite significant also, and made us to know that, okay, this treatment residual are quite okay to use as a remediation technique for the sorption of PFASs that may be leaching out when biosolids are applied to our agricultural fields. The summary of my finding was the ACH was effective for the sorption of PFAAs from biosolid-derived pore water. The sorption of the PFAAs bound to the ACH treatment residual was low for all the compounds, especially the long chain compounds, PFOS and PFOA and PFNA. So this generated sorption and desorption data suggests that the ACH-WTRs can function as an amendment in biosolids to attenuate PFAS release. So there are still some further works going on here. Column studies are underway to be able to quantify the leachability, the leachate coming out, where we're going to assess transformation and some other things that may be going on in the pore water biosolid matrix. So that ends my presentation. I'll be open to questions.
We do have about 5 minutes for questions. Reminder that you can type your questions in the Q&A button on the toolbar. While people are thinking, so I'm not a PFAS expert, so I was wondering if you had tested PFAS with side chains as opposed to just having just a straight chain.
Yeah, we did that for some of our compounds like PFOS, PFHxS, both the linear and the branch chain were checked. So what you see here is for total PFAS, both the linear and the branch chain.
Okay. Did you see the same results for the same chain length for single chain and branched?
Yeah, the results were similar. There was
Okay.
not a significant difference.
Okay.
Okay, we have a question. According to the OECD, there are at least 4,730 different PFAS with at least 3 perfluorinated carbon atoms. A U.S. Environmental Protection Agency toxicity database, TSSTOX, lists 10,776 PFASs.
Okay.
Are there any PFAS in the water treatment residuals?
Yes, there were, but they were significantly low. And that was the first experiment we did, which was to check out the PFASs that were bound to the treatment residue initially. They were significantly low, and we did an initial desorption experiment to see if they were releasing out, which was not significant. And that gave us the confidence to go ahead with the experiment.
Why do you think? Go ahead.
Why do you think is the reason for the low desorption of the long chain PFAS? Okay, for the low desorption of the long chain PFAS, I mean, I could think about it in the sense of hydrophilic, hydrophobic forces at play. Longer chain compounds are would prefer to sorb more to the treatment residuals, which may contain stuff like organic matter, which we are going to really deal with in the column studies. So the longer chain, like may prefer to sorb and attach more with the organic matter that may be in the treatment residual, unlike the shorter chains, which are more hydrophilic.
What are the PFAS preferentially absorbed into the biosolids?
Into the biosolids? Well, I will assume this is into the treatment residual because I wasn't checking PFAS absorbed into the biosolids. So into the treatment residual, it was the longer chain compounds were preferentially absorbing. And again, also due to like the longer chains are more hydrophobic, and so they preferentially prefer to sorb more to the, whether it's a biosolid or the treatment residual that's going to contain more organic matter, unlike being in the aqueous phase, which has less organic matter in them.